The system is the same because it's the same final and initial state. Okay. So the entropy change of the system is always the same initial and final states. The entropy change of the surroundings, though, is minus the actual Q over T, because the surrounding sees it. As far as the surrounding is concerned, everything's reversible because it doesn't see the irreversible process. All it sees is a transfer of heat. So now I have to calculate the actual entropy. So the actual heat is, the actual work is minus P external delta V, which is less negative, of course. Delta U is still 0 because it's still an ideal gas at constant temperature. Okay, so the actual heat now is less than it was before, so the entropy change of the surroundings is less negative, and so the total entropy change is now positive. So it's a spontaneous process because it's expanding against. Okay. But the important point is the entropy change of the surroundings. Whether you calculate the entropy change for a reversible path, once calculated, it's the same for every path. It's the entropy change of the surroundings that change as things go from reversible to irreversible. Okay, we had number 3. You had 2 heat reservoirs. One's at 1,000, one's at 200. I think you can resist heat transferred from high temperature to low temperature. That's irreversible over T. The entropy change of one is 1,000 over that T. The entropy change of the other is minus 1,000 over 473. That's why you have T in the denominator, so the total entropy is always positive if heat flows downhill. Number 5 was Troughton's law. Okay, number 5, I didn't tell you Troughton's law. The boiling point of zinc is 1184 Kelvin. Using Troughton's law, calculate the entropy and enthalpy of vaporization. Okay, Troughton's law is the following. I didn't talk about that. Troughton's law of la règle de Troughton says that for all materials, the entropy of vaporization is around 88 joules per mole Kelvin. Okay, because you're going from a liquid to a gas. And so most materials, if you go from a liquid to a gas, it's about the same change in disorder. You're disrupting the whole thing entirely. Okay, so I mean, this is plus or minus 20–30%. It's not very accurate. But I mean, the entropy of vaporization is not going to be 300, it's not going to be 10, it's going to be sort of actually 88 because it was usually given in calories of 20 or something. It's not that accurate. Okay, so the entropy of vaporization is always roughly around there. If you want a rough idea of the heat of entropy of vaporization going from liquid to a gas, for most materials it's of the order of that, give or take 20–30%. Okay, so the entropy of vaporization is T over delta S at the boiling point. At the boiling point, the delta G of vaporization is 0. Okay, so delta G is delta H minus T delta S. At the boiling point, the liquid is in equilibrium. This is the standard entropy, meaning to go to a gas at 1 atmosphere. Okay, so for the liquid goes to the gas at 1 atmosphere, that's delta G naught of vaporization, and at the boiling point, the delta G naught is 0 because the boiling point is the point at which the liquid's in equilibrium with its vapor at 1 atmosphere. So at the boiling point, delta H is T over delta S, so the heat of vaporization is about 104 kilojoules per mole, give or take 20–30%. So if you find a material that has a very high boiling point, the boiling point's high not because the entropy is very different, but because the enthalpy of vaporization is different. Enthalpy is the energy to vaporize it. If a system has very strong bonds, it has less tendency to vaporize, so the heat of vaporization is higher, so the temperature of vaporization is higher. The change in entropy, however, is more or less the same. So this is just a very rough rule to give you an idea of the heat of vaporization. If you know the boiling point, or you do it the other way around, if you know the boiling point of a material, which is easy to measure, you can get a fairly good estimate of the heat of vaporization, roughly. There are other rules of Troughton for different classes of material which are more accurate. This is like a general rule, I say give or take 30–40%, but I mean if you consider only metals, only transition metals, only polar organic molecules and so on, then you can have a règle Troughton that's a little bit more restricted. You have lower error limits to it. Okay, but the point is when things have a high boiling point, it's not because of the entropy, it's because of the heat. Things have a low boiling point, it's because the bonds are weak, not because there's an entropy. The entropy when you form, it's basically the entropy of forming the gas is more or less the same. Increase in disorder. number 6 was, okay, 2 cases of solidification. We have 1 mole of zinc, should be doing it here, 1 mole of zinc goes from liquid to solid in equilibrium with the surroundings at 420 degrees, which is the equilibrium melting point. That's what equilibrium melting point means. Equilibrium melting point means the solid and the liquid are in equilibrium with the surroundings. The solid and liquid will exist there. It's a reversible process. It can go one way or the other. Or here we have 1 mole of zinc, metastable. You know, if you don't have any nucleation sites and you cool a liquid slowly, you can easily supercool it, have the liquid existing 20 degrees below the melting point. Supercool. You can supercool water easily about 5 degrees. Metals are easier to supercool. You can supercool a metal up to 50 degrees sometimes if you have it in a clean container without any nucleation sites and you don't agitate it, you can sometimes cool it down way below the melting point. Okay, so now we have a liquid zinc going to form the solid at 400 degrees. For each case, calculate the entropy of the zinc, the entropy of the surroundings, and the total entropy change. Okay, so zinc melting at its melting point, solidifying at its melting point, and zinc solidifying 20 degrees below the melting point. Okay, so we go to number 6. Okay, so I'm drawing here what I call a thermodynamic cycle. I didn't talk about that. Let's say here, this is zinc liquid at 420, and this is zinc solid at 420. So here, if this is the initial state, this is the final state, that zinc going from the initial to the final state at 420 degrees. Here we have zinc at 400 going to form the solid at 400. So this is the reaction at 400 degrees. This is the reaction at 420. All right, so let's consider first of all the reaction at 420. The entropy at 420 is the reversible heat over T. At 420, it's a reversible reaction. Reversible reaction is a reaction which occurs at equilibrium, and at 420, the liquid and solid are at equilibrium. Okay, the heat of solidification is minus 17. This is solidification, not fusion, so the heat of solidification is minus 1740. And so the reversible heat over T is minus 2.5. This was actually in calories. Okay, calories per mole Kelvin. Some of these problems go back years and years. Calories per mole Kelvin. Okay, it's negative because the solid is a more ordered state than the liquid. Okay, so the system is becoming more ordered. The entropy change of the surroundings, or the entourage, is minus Q over T. The actual heat is 1740, so it's plus 2.5, and the total entropy is 0 for a reversible process, as you would expect. Now, let's say the zinc liquid goes to the zinc solid at 400 degrees. First of all, I want to calculate the enthalpy at 400 degrees. So the enthalpy at 400 degrees. Okay, I've got to get from here to here. Now the enthalpy changes as the enthalpy of the products minus the enthalpy of the reactant. So what is delta H for this reaction? What I do is I'll find a path for which I can calculate the heat. You can't find the heat of this reaction at 400 degrees in the tables, but I'm going to calculate it. So what I'm going to do is I'm going to go any path. Delta H is independent of the path. So any path I take from this state to this state is going to have the same delta H. If I go directly at 400 degrees, or what I'm going to do is I'm going to first of all heat the liquid to 420, react it at 420, and then cool the solid down. It's exactly the same total delta H. The sum of these 3 delta H's will be the same as this delta H because H is a property of state. So this is the enthalpy of heating the liquid, which is the integral to Cp liquid dt from 673 to 693. This heat here is minus the integral of Cp dt from the same limits, and this is delta H at 420, which we know. Okay, so the total delta H at 400 is this, which is the integral of Cp liquid dt, this, which is minus the integral of Cp solid dt, plus the delta H 420, and it comes up to minus 1730. Now, there's no reason why this is more or less negative than this. It depends obviously on the relative values of Cp liquid and Cp solid. If they're the same, so the first approximation, delta H, of fusion changes very little with temperature. Okay, this could be, so here it's a little less negative, but it could be a little more negative. It doesn't. Okay, but because it's the difference of this, it's only the difference of the Cp. So the heat at 400 is slightly different, but not much. Now let's calculate the entropy change at 400. The entropy change at 400, entropy is also a state property. So the entropy change at 400 is the same. I calculate the entropy for each of these three steps and then add them up. Okay, that'll be the same entropy as going directly. So the entropy of heating something, as you recall, is simply the entropy of heating something is the integral of Cp over T dt. So this is the integral of Cp liquid over T dt is the entropy to heat the solid, minus Cp solid over T is for cooling back down that's for heating the liquid, this is for cooling back down the solid, and this is the entropy that we calculated in the first step at 420. So once again, you'll find that this term here is quite small because it only depends on the differences of Cp, and so the entropy change at 400 also is quite similar to the entropy change at 420. And once again, it could be more or less. So the entropy, the only reason this is slightly less negative is because Cp liquid is a bit greater than Cp solid, but it could be the other way around. So that's not a general rule. So the entropy at 400 is almost the same as the entropy at 420. To a first approximation, you could assume it was. What's different, however, what makes the reaction spontaneous or irreversible at 400 is the entropy change of the surroundings, which is minus delta H over T for the real reaction. And the delta H over T is 1730, but it's the T down here that's different, because now you're dividing by 673. Okay, up here you divided the entropy by 693. Down here you're dividing it by 673, so the entropy change of the surroundings is what's different. So the total entropy now is positive. Okay, so I mean, to calculate things exactly, you want to calculate this here. It's not exactly the same as 1740 and so on, but the main difference is in the denominator down here, which means the total entropy is positive, which says that if you have a supercooled liquid at 400 degrees and it starts to solidify, it solidifies rapidly and irreversibly. It's not at equilibrium. If you were to do the same cycle but at 440 degrees, then you would do the same thing, but you'd find delta S total was negative, meaning the liquid will not go to the solid at 420. It's spontaneous the other way. Any questions about series 4? Just general concept of the entropy. All right, so let's go to series 5. Okay, chemical equilibrium, assuming section 5 or series 5 is chemical equilibrium, but so far only the solids and liquids are all pure, but the gases can change. So here we have number 2, starting with number 2. This was a bearing, a copper molysulfide bearing. Let's say it's a composite. So you have particles of molybdenum sulfide, which is a hard ceramic, and a matrix of copper, which is ductile. So ideally then you got a composite with combines the best properties of both. However, the problem is that molybdenum sulfide could react with the copper. So will the molybdenum sulfide be reduced by the copper? At 727, suppose that all the phases are mutually insoluble, there's no solutions, and I give you the Gibbs energy of formation of dissociation of copper sulfide, which is the negative of the Gibbs energy of formation, and the same thing for moly sulfide. Okay, so in this case the reaction equilibrium is this one. So I said, will the molybdenum sulfide be reduced by the copper? So will copper plus moly sulfide form copper sulfide plus molybdenum? That's what you want to know. This delta G then, using Hess's law, is the sum of these delta G's, or it's this one. This reaction is this reaction minus 3 times this reaction. So the delta G standard, this is the standard Gibbs energy, for this reaction is positive. Now the standard reaction is the reaction among the reactants and products in their standard states. The standard states are the pure solids. In this case, everything is a pure solid. So delta G is in fact delta G naught. Okay, so delta G is the same thing as delta G naught, and it's positive, so there will be no reaction. Okay. Number 14. Number 14. Okay, number 14 is, calculate the heat, entropy, Gibbs energy in K at 600 degrees for the oxidation of aluminum. And given this, so the data, These are the data that you would find in tables, or these are the actual numbers that are stored in the FactSage database. Okay, so you have the enthalpy at 298, that's what is stored, the standard enthalpy at 298 for that reaction. The entropy, absolute entropy is at 298 for the reactants and products. And normally you would have a heat capacity as a function of temperature, but I've simplified life by telling you that the heat capacities are constant. Okay, so it's just to show you what happens when you do FactSage, how it calculates it out. So you can make a mistake in this. I'll show you what this normal mistake is, but okay, once again, I try to look at this in terms of what I call a thermodynamic cycle. Here you have the reaction at 298, reactants and products at 298. Here you have the reaction at 600 degrees. Okay, so all of these products, the delta H, the delta whatever at 600 degrees is the sum of these deltas plus this delta plus this delta. Okay, so the data are tabulated at 298. So we're trying to go from reactants at 600 to products at 600, so I take a hypothetical path. First of all, I cool down the reactants, react them at 298, and then heat the products back up to 600. And the delta H for the direct reaction is the sum of these delta H's for the hypothetical path. Okay, so delta H at 600 then is delta H at 298, plus the integral of Cp to heat the aluminum, minus the integrals of Cp to cool the solids down, and you end up with that. The entropy at 298 is the same thing. It's the entropy, the entropy at 298. Now the entropy you had the absolute entropy. So the entropy at 298 is the entropy of the product, alumina, minus the entropy of the reactants. So this is your entropy at 298. And then to get the entropy at 600, you do the same cycle. You first of all cool down the reactants. Here's the entropy to delta Cp is the same. We call this delta Cp because it appears so often. Delta Cp is Cp products minus Cp reactants. Okay, so the delta H at 600 is delta H 298 plus the integral of delta Cp dt. The delta S at 600 is delta S 298 plus the integral of delta Cp over T dt. So we end up with the entropy at 600 degrees. The Gibbs energy at 600 degrees then is delta H at 600 minus 600 times the entropy of 600. Delta G is delta H minus T delta S. Okay, so that's delta G of the reaction. And delta G standard is minus RT log K. So that's the equilibrium constant, which is, of course, gigantic. Any questions about that one? Okay, that's what's happening internally in the software. In fact, say the numbers that I showed you there, H298, delta H298, entropy at 298, and Cp expressions as a function of T are stored in the database, and this is how the calculations will be carried out. Number one. Okay, number one, oxidation of nickel. Will nickel be oxidized or will NiO be reduced? If a mixture of nickel and nickel oxide is in an atmosphere composed of 15% CO2, 5% CO, and 80% nitrogen. Okay, so in a container you put nickel and nickel oxide, and the container contains 15% CO2, 5% CO. Of course, gas compositions are always molar or volumetric if it's ideal gas. Which way does the reaction go? Does the nickel get oxidized or does the NiO get reduced? And I give you here the Gibbs energies of formation, the Gibbs energy of this reaction and the Gibbs energy of this reaction at 1,000 degrees. Now this is trivial. I just want to show you three ways that we do it. Okay, this is the actual reaction. The nickel plus CO2 will form NiO plus CO. The Gibbs energy of this, the delta G standard of this reaction is this Gibbs energy minus this one by Hess's law. So the Gibbs energy of that reaction is 47,350, which is minus RT log K. So we can calculate the equilibrium constant, which is PC over PCO2 at equilibrium. So this equilibrium constant is the ratio at equilibrium. The Q I call this is the reaction constant. Sometimes Q is called the reaction quotient. Q is the actual ratio. This is the ratio that will give you equilibrium. The actual ratio is 5 over 15. Okay, which is 0.33, which is greater than K. Okay, so the actual ratio of CO over CO2 is greater than the equilibrium ratio. So the CO over CO2 ratio is too large for equilibrium, so the reaction proceeds to the left. Or if the other way to write it would be delta G of the reaction is equal to delta G naught plus RT log Q, where Q is the actual ratio. Delta G naught is minus RT log K plus RT log Q. And so delta G of the reaction is minus RT log K, or plus, minus RT log K over Q. Okay, so if the actual ratio is equal to the equilibrium ratio, delta G is 0, and it's at equilibrium. In this particular case, Q is greater than K, so this is negative. This becomes a positive delta G, so delta G is positive, so the reaction goes to the left. Okay, that's method 1. This as well, that was method 1 I did here. Q is greater than K. That's also called the principle of Le Chatelier. If you displace an equilibrium in one direction, the equilibrium tries to go back. Okay, so here the thing was in equilibrium at this ratio here, at the equilibrium ratio of 10 to the minus 3. You displace the equilibrium to the right. The reaction tries to go back to equilibrium. That's the way Le Chatelier originally talked about the whole thing. So you just compare equilibrium constant to the actual ratio and see which one's bigger. Or you can do it this way, which is really the same thing. It's exactly what I did here. Delta G is delta G naught plus RT blah blah blah. So that's positive, so nickel oxide is reduced. And the third way you look at it is the following, and I think it's worthwhile to look at this is the hypothetical way of looking at it, which is probably the way, the actual reaction is the reaction, this is the actual reaction here. Okay, the container contains, for all intents and purposes, hardly any oxygen. Oxygen doesn't participate in it. Nickel is, CO directly attacks the nickel oxide to form nickel plus CO2. This is the mechanism of the reaction. But we can do the calculation this way. Let's suppose there was oxygen. So nickel plus oxygen forms nickel oxide, delta G naught minus RT log 1 over PO2, where this is the equilibrium oxygen pressure for this reaction. And that's something times 10 to the minus 16th atmospheres. So for nickel and nickel oxide to be in equilibrium, the oxygen pressure has to be this. If the oxygen pressure is greater than this, nickel will be oxidized. If it's less than this, the nickel oxide will be reduced. So this is your equilibrium oxygen pressure for this reaction. Now we calculate, we say in the container you have CO and CO2, but clearly in the gas phase, in the homogeneous gas phase, there will be an equilibrium. CO2 will dissociate slightly to form CO and oxygen, and at equilibrium there will be an oxygen pressure. And the oxygen pressure is given by the equilibrium constant for this reaction. Okay, so there's the equilibrium constant for this reaction. I put in PCO2 over PCO is 15 over 5, and I calculate the equilibrium oxygen pressure. So this is saying that the gas phase fixes an oxygen pressure of 10 to the minus 20th atmospheres. The equilibrium oxygen pressure for this reaction is 10 to the minus 16. So clearly the equilibrium oxygen pressure is less than this one, so the nickel oxide will be reduced. Now this is purely hypothetical. 10 to the minus 20th atmospheres of oxygen is 1,000 molecules in a... Okay, the oxygen is not participating, there's no molecules of oxygen participating in this reaction. But you look at this as a potential of oxygen. The partial pressure is the oxygen potential. And you simply want to know, is the oxygen potential of this reaction higher or lower than the oxygen potential for this reaction? And this is usually the way people will talk about it. They won't do the whole thing. They'll say, well, the atmosphere has a PO, the oxygen pressure in the atmosphere is 10 to the minus 20. It isn't really, there's hardly any oxygen there, but the oxygen potential in the atmosphere is 10 to the minus 20. The oxygen potential for this equilibrium is this, so this is less. And of course they're all exactly the same thing. Okay, so three ways of Okay, so when people talk about an oxygen pressure being 10 to the minus 20, they're not supposing that oxygen is really participating, it's just a way of looking at the whole thing. Okay, I know you've all seen this kind of stuff, but I think these are like fundamental things, so what the hell. Number 4, nickel. Solid nickel is put in an atmosphere where pH 2 over pH 2S is 50. Will there be a formation of a sulfide? Sulfide. Well, I considered this reaction up here, nickel plus hydrogen. It's the same as number 1, but now it's with sulfide. So I looked at the first, the nickel plus hydrogen sulfide forms nickel sulfide plus hydrogen. I calculate delta G is delta G naught plus RT log pH 2 over pH 2S. The delta G naught is the sum of those two reactions, and it's the same as number 1. The delta G is negative. So the delta G is negative, so NIS will be formed. So NIS will be formed, but the question was, will NIS2 be formed? So I have to consider the second reaction as well. So I take the delta G for this reaction, take RT log, and I calculate it's positive, so the second reaction will not occur. So NIS is the equilibrium product. That's not really the right way to do it. Suppose I found that both, because I could find that both delta G's were negative. If I find that both delta G's are negative, what does that mean? Does that mean that they both sulfides are formed? This is a good question. It's phase rule.
The one is much more negative?
The one that's more negative, yeah. Of course, you have to be careful when you say more negative because you got to put it on the same molar basis. So the best thing is to write out the reaction nickel sulfide, or Ni plus H2S forms Ni3S2 plus H2. The delta G for this reaction will be this one minus this one. You got to balance it somewhere. You can balance it. Once it's balanced, the delta G for this balanced reaction will be this one minus this one. And that's going to be either positive or negative. So you can't have two sulfides. You can't have the two solids. You'll have one or the other, but not both. Holmes. Oxygen is injected into a bed of coke at a 1600. When equilibrium is reached, the gas phase consists of CO, CO2, and oxygen at a total pressure of 1 atmosphere. It's in equilibrium with the coke. Calculate PCO, CO2, oxygen at equilibrium. And you're given the delta G's of formation of CO and CO2. Standard Gibbs energies of formation at that temperature. Okay, so you have, well, this is like a gas furnace. You have a bed of coke at 1600 degrees. You have an equilibrium between CO, CO2, and oxygen. What are the equilibrium pressures at equilibrium with the solid graphite? Okay, so we go to all right, so there you go. CO plus CO2 equals 2CO. So that reaction's at equilibrium, because we said if the whole system's at equilibrium, then any subreaction you can write must also be at equilibrium. So if the whole thing's at equilibrium, then any reaction that you can write will be at equilibrium. So this is at equilibrium. The Gibbs energy change for this reaction is a sum of, again, Hess's law. It's 2 times the Gibbs energy of formation of CO minus the Gibbs energy of formation of CO2. We can calculate the equilibrium constant, which is this, and the equilibrium constant will be PCO squared over PCO2. This is a very classic reaction called the Boudoir reaction. PCO squared over PCO2. The sum of the partial pressures equals to 1. We know that the partial pressure of, you should know the partial pressure of oxygen is going to be very low. If your atmosphere is in equilibrium with carbon, it's going to have an extremely low oxygen pressure. Okay. So you can assume that PO2 is extremely small. Hence, if PCO squared over PCO2 is 22,000, PCO is clearly going to be much bigger than PCO2. So for all intents and purposes, PCO is 1 atmosphere. And PCO2 then is calculated as 10 to the minus 5th. Okay. Okay, so PCO is 1 atmosphere for all intents and purposes. PCO2 is 10 to the minus 5th. You want to calculate the oxygen pressure, so well, let's go back to this. We can go to this reaction. No, go to this reaction. carbon plus oxygen. So this reaction is also in equilibrium. The delta G naught is minus RT log K. PC over PO2 to the 1/2 at equilibrium. PCO we've now shown as 1 atmosphere. So the oxygen pressure is 10 to the minus 16th. So that assumption was justified. But he said, well, how do I know if it's a good assumption? We'll make the assumption and then do the calculation and see what happens. If you end up with PO2 is large, then you know you made a bad assumption. Okay, so you don't have to know that PO2 is low, but it saves you time if you do. Okay, so everything's at equilibrium, and basically, so this is what happens in a blast furnace at high temperature. The atmosphere consists of CO, CO2, and oxygen, but this reaction is shifted very strongly to the right at high temperature. So at high temperature, the atmosphere is mainly CO, there's very little CO2. If you were to repeat this calculation at, say, 500 degrees Celsius, you would find the opposite. You would find that this reaction was shifted to the left, and the Gibbs energy change for that reaction, and the CO ratio, the K would be much smaller. Okay, so at high temperature, this reaction is shifted to the right. At low temperature, this reaction is shifted to the left. So at the lower levels of the blast furnace, the CO with the gas is almost all CO, but as you move up higher and higher in the furnace to the lower temperatures, the ratio of CO to CO2 drops, and at a certain point the CO2 is actually at equilibrium with the carbon, with the graphite charge that's coming down. The coke charge that's coming down is actually more CO2. So the top gas coming out of your furnace contains quite a bit of CO2. Now, okay, why is this, tell me then, why is this reaction shifted to the right at high temperature? Well, I'll explain. What you got to do is delta G naught is delta H naught minus T delta S naught. So the delta G becomes more negative at high temperature. Okay, if the entropy change is positive. Why is the entropy change positive in that reaction?
Volumes of gas, two volumes of gas.
Yeah, you got two volumes. The gas has a bigger entropy than the solid. You have 2 moles of gas on the right, 1 mole of gas on the left. So, all right, let's look at number. What was that? It was 11. Number 12. Molybdenum heating element. Molybdenum is utilized as a heating element in an electric furnace to prevent the formation of molybdenum oxide, MoO2. You have to keep the element in a reducing atmosphere. The only gas that's available is wet hydrogen, which is hydrogen which has been saturated in water at 25 degrees. Can you use this gas to produce a reducing atmosphere or not? Straightforward. This is the reaction you're trying to avoid. You're trying to avoid molybdenum. You're trying to keep it from oxidizing, but you got some water vapor in the gas. Is there going to be enough water vapor to oxidize the molybdenum according to this reaction? Okay. Wet hydrogen is just very easy to produce. That's all. It's produced by electrolysis. You don't have to dry it. Delta G standard for the reaction is given by Hess's law is -9. The water pressure, the vapor pressure of water is 24 over 760. What did I give you? The vapor pressure of water in Okay, the vapor pressure of water is 24 torr. Torr is a millimeter of mercury, so the partial pressure of water is 24 over 760. Remember, equilibrium constants, you always got to do it in atmospheres or bars. The partial pressure of hydrogen then is 1 minus the partial pressure of water, if you're assuming the total pressure is 1 atmosphere. Okay, so for this reaction then, delta G is delta G naught plus RT log pH2 over pH2O squared, and then you can calculate it as being positive, so the molybdenum will not be oxidized. The other method is again just comparing the oxygen pressure. For this reaction, the oxygen pressure from just like question number 1, the equilibrium oxygen pressure from the equilibrium constant is 10 to the minus 21st. The equilibrium oxygen pressure from a mixture of H2H2O is 10 to the minus 23rd, so this is too low, so you don't get any oxidizing. All right. If you have any questions, don't hesitate to ask. I'm just going quickly because I assume you all are very happy. Mixing an ox, this shows you a little bit about, well, you don't really have to do this way anymore, but it gives you an idea of how the mass balance comes into the equilibrium constant. This is a mixture of carbon dioxide and strontium with carbon. When you heat a mixture of strontium oxide, carbonate, strontium oxide and carbon, the gas phase has in equilibrium with the three solids. Let me draw the diagram here. So we consider a container down here. I put strontium carbonate. This is a solid, strontium oxide and graphite. And the gas phase is in equilibrium with it. At say 850 degrees, you measure total pressure. P total is 171 torr. Okay, you measure a total pressure of 171 torr when the gas phase is in equilibrium with it. The gas phase has got CO, CO2, and of course there's going to be some oxygen. You then do the same experiment, but this time you just put strontium carbonate, strontium oxide, and no carbon, and now you measure the total pressure. And in this case, the total pressure is equal to 2.47 torr. And the question is, what is the Gibbs energy change? Standard Gibbs energy change for that reaction. There's actually a way of measuring the Gibbs energy change for that reaction. Okay, it's clear what happens. Okay. Calculation is fairly straightforward. It's the principle that maybe seems simple, but gotta think about it. 6. Okay, I'm starting with actually the second reaction. If only strontium carbonate is there at the beginning. Well, actually, okay, I said what I think I said. We didn't even have any strontium oxide, but we know what's going to happen. If I start with just strontium oxide and heat the thing and let it reach equilibrium, you know that the strontium carbonate is going to dissociate to form strontium oxide plus CO2. That's called calcination. If this was calcium, it's calcination. With strontium, it was in the same group of the periodic table. That's calcination. Okay, so this is the reaction that happens. So you end up, after it dissociates, you end up with strontium oxide, and you end up with CO2. Now the CO2 will also partly dissociate to form the CO2. Of course, will also partially dissociate to form the CO and oxygen, but this doesn't really matter at this point. The point is, for this first reaction now, this equilibrium is found in this experiment here, where there's no graphite. The total pressure now, okay, for all intents and purposes, the total pressure will be the pressure of CO2. Actually, you could calculate this out later. You'd find that these partial pressures are negligible. It's mainly, almost totally CO2. So, work it out. Once again, if you don't know to make the assumption, you make life harder for yourself, but you make the assumption, see what happens. If you don't get it right, well then you have to do a more complicated calculation. But so total pressure is, for all intents and purposes, PCO2. Putting that into atmospheres, you get 3.25 times 10 to the minus 3 atmospheres. So that's the equilibrium constant for reaction 1. Now if you do the same experiment, but you put carbon in there, okay, then you find you get a higher pressure. Okay, because now you're also getting this reaction. The CO2 is reacting with the carbon to form CO. Okay, and the equilibrium constant. Now, so if the three solids are present, K1, which is 1. Yeah, okay. If the three, here's the most important point is, if the three solids are present, you now have these two equilibria going on, but the whole system is at equilibrium. So if the total system's at equilibrium, every partial equilibrium is also maintained. So the whole system's at equilibrium, but the CO2 is still at equilibrium with strontium oxide, obviously, or else this reaction would be going. Okay, so Total equilibrium indicates all partial equilibria are also satisfied, so the important thing is that even though you have the carbon there and the total pressure has changed, the CO2 partial pressure is exactly the same as it was here, because it's determined by this equilibrium. Basic principle of chemical equilibrium. Here you have this solid, and CO2 are at equilibrium. It doesn't matter what other gases are present. This is the equilibrium CO2 pressure. Okay, so you put in these other gases. Now you have a lot of CO form, a higher pressure going up, but the partial pressure of CO2 is still determined by this equilibrium. Okay, so PCO2 in the second case, when you have the carbon present, is exactly the same as it was in the first case. And so the CO pressure is simply the total pressure minus the CO2. So the total pressure now in this case is much higher, it's 171. The CO2 pressure is still 2.47, so now you have the CO pressure. Okay, so now when this whole system is at equilibrium, you have now two reactions at equilibrium. You have this reaction at equilibrium, which fixes PCO2. You have this reaction at equilibrium, which now, given the PCO2, fixes PCO. Sorry, not that reaction. Not that reaction. I'm sorry, this reaction. Carbon plus CO. Where are we? Carbon plus CO2 equals 2CO. So this reaction is also at equilibrium. This PCO2 is the same, 2.47. The PCO is. So you now know what PCO2 is from the first reaction. You know what PCO is from the second reaction. So the equilibrium constant for this one, K2, is PCO squared over PCO2, so it's 15.414, and delta G naught is then minus RT log K. So in this experiment, the two experiments together, you have actually succeeded in measuring the standard Gibbs energy change for this reaction. Putting it the other way, you've set up this equilibrium between carbon, CO2, and CO. You fix the CO2 pressure by this equilibrium. Okay, and that way that then permits you to measure the total pressure. You measure the PCO. You can also calculate the amount of oxygen, but it's trivially small. Okay. This is actually, I mean, some of these seem simple. This is like a kind of fundamentals of chemical equilibrium, I feel like. The whole system's at equilibrium, so any reaction that you can write is also going to be at equilibrium. Okay, is everybody happy with that one? So it's a simple calculation, but I would say it's an important one to be sure you understand the principles involved.
The PCO part, PCO is equal to P total minus PCO2. Can you just explain that?
You mean here?
Yeah, just.
Well, you measure the total pressure.
Yeah.
The partial pressure of CO2 is 2.47. It's the same as it was before.
Okay.
You measure the total pressure, the difference has to be. There's only two gases.
Okay. CO2.
Okay, number 7. A piece of phosphorus pentachloride solid, 3.6 grams, is put in a container. You close the container under vacuum, and then you heat it up. So I take a closed container containing 3.6 grams of PCl5. You heat it up, the PCl5 completely vaporizes, there's no solid left. You get PCl5 gas, and the PCl5 gas then partially dissociates to form PCl3 plus chlorine gas. So you end up with a homogeneous gas phase at equilibrium containing PCl5, PCl3, and chlorine. At 200 degrees, the solid completely vaporizes, blah, blah, blah. Calculate the equilibrium constant of this dissociation reaction. Okay. And the total pressure measured at 200 degrees is 1 atmosphere. So we have a pressure gauge on here, we heat it to 200 degrees, we measure the total pressure, and I ask you to calculate the equilibrium constant for that reaction. This is a equilibrium, this is an example, simple example of an equilibrium constant calculation involving a mass balance. Once again, now these are old questions. Once you have facts age or this kind of stuff, you don't have to do it this way, but you should understand what's going on. So, the total number of moles of PCl5 was 3.6 over its molecular weight. And I said there were 3.6 grams. That's the total number of moles of PCl5 you put in at the beginning. This is the molecular weight of PCl5. So you have 0.0173 moles of PCl5 at the entrance. This is entrance, the input. So the input was 0.0173 grams of PCl5, and at the beginning you had no grams of PCl3 and no moles of chlorine. This is in moles. 0.0173 moles. Then the reaction attains equilibrium. So the reaction is PCl5 forms PCl3 plus Cl2. And I'm assuming if you form X moles of this, you will also form X moles of this, and you will form minus X moles of this. Okay, so you write down here the total number of moles at equilibrium. So that's X, and that's 0.0173 minus X when the thing reaches equilibrium. You also have to calculate now the total number of moles at equilibrium, which is this plus this plus this. Okay, now you can calculate PV is nRT, P total V is N total RT. So P total, I said, was measured at 1. The volume was 1 liter, that was given to you. This is the total number of moles, RT. Okay, R is 0.082 if this is a liter atmospheres. So then you can solve this to calculate X. You can calculate what X was at equilibrium. Okay. So now you can calculate your partial pressures. Your partial pressure of PCl3. The partial pressure by Dalton's law is always equal to the partial pressure of PCl5 is the number of moles of PCl5 over the total number of moles times the total pressure. So Dalton's law is the partial pressure of I is the number of moles of I divided by N total times P total. Okay. Be careful in this. Some of these questions you tend to assume that P total is 1. In this question it is, but it isn't always. And this is the total number of moles of gas. Because if they're solids, this is the mole fraction in the gas phase. Okay, so this is the number of moles. This is partial pressure in the gas phase, is the number of moles in the gas phase divided by the total number of moles of gas, not total number of moles of the system. Total. In this case, of course, there's nothing but gas. So the partial pressure of PCl5 is the number of moles of PCl5, which is here, divided by the total number of moles, which we just calculated up here, times the total pressure, which is 1 atmosphere. That's the partial pressure of PCl5. You do the same thing for PCl3, which of course is obviously equal to the same as PCl2. Number of moles, total number of moles, 329. And for the reaction that we're interested in over here, the partial pressure, the equilibrium constant is the ratio of the partial pressures at equilibrium. And then delta G standard is minus RT log K. Okay, so it's taking a mass balance into account in the calculation. Okay, this is similar to the okay, this is similar to that one I did with the nickel sulfide and the Ni3S2. Back number 5 or something. I said that the you can only have. I said you're gonna form a sulfide. You can form nickel sulfide. You can form Ni3S2, but you can't form more than one. Okay, so now it's the same thing here. This is the roasting of nickel sulfide. So you take nickel sulfide NiS, you put it into air, and NiO, the nickel sulfide 2 it's the mineral NiS is heated in presence of air in order to convert it to NiO. SO2 is produced as accumulates in the reactor. As a matter, it depends now on the partial pressure of oxygen and SO2 that are in the reactor at equilibrium, because the solid phase could be NiS, it could be NiO, or it could be NiSO4, depending on what your oxygen and SO2 pressures is, but it's only going to be one of them. So during a roasting at 1,000 degrees, you find that PSO2 is 1 atmosphere, and PO2 is 10 to the minus 2 atmospheres. So what would be the solid phase at equilibrium when the SO2 pressure is 1 atmosphere and the oxygen pressure is 10 to the minus 2? And these are the Gibbs energies for the various reactions. So are you going to get NiS? In other words, there's no roasting. Are you going to form NiO, which is what you want, or are you going to form NiSO4, which in this question is what you don't want? Okay, so you control the SO2 and oxygen to get the one product that you want, and then the okay, so there's many different ways of doing it. I've chosen to do it here in terms of the how did I choose to do it here? In terms of the oxygen pressure. No, sulfur pressure. Okay, so the PSO2 and the PO2 are given. The PSO2 is 1 atmosphere, the PO2 in the atmosphere is 10 to the minus 2, but what is the equilibrium sulfur pressure in the gas atmosphere? What is the equilibrium sulfur pressure fixed by this homogeneous gas phase equilibrium? So the SO2, the oxygen, and the S2 in the gas are all at equilibrium. So delta G0 is RT log K, K blah blah is equal to the ratio. Here I put in PSO2 and PO2 and I calculate the sulfur pressure. So the equilibrium sulfur pressure is 10 to the minus 27. Now we're all set to go. Now we have a gas phase in which we know the SO2 pressure, we know the oxygen pressure, and we've calculated the sulfur pressure. Okay, so now we consider the first reaction. The Gibbs energy change for this reaction is delta G naught plus RT log PO2 to the minus 1/2. It's negative. So this reaction will go. So you won't get nickel, you'd at least get nickel oxide. But you got to check some of the other possibilities. Will nickel form nickel sulfate? So delta G is delta G naught is, so for this reaction, it's negative. So you should get nickel sulfate. And so for this reaction, it's positive, so you won't get nickel sulfide. But are you going to get nickel oxide, or are you going to get nickel sulfate? So delta G2 is less than 1, is less than 3. So nickel sulfate is produced. But the important thing is, let's look at it this way, so in principle, NiO, you're not going to get NiS because it's negative, it's positive, but you're going to get one of these. So you got to consider the exchange reaction. Nickel, SO2, oxygen, and NiSO4. Delta G for this reaction is delta G2 minus delta G1 is negative. Therefore, if nickel oxide was produced, it will react to give nickel sulfide. Okay, so according to this reaction, you should get nickel oxide, but the nickel oxide will react to form the nickel sulfide. You're only going to get one solid that's going to be the most stable. You got to consider. If there was no such thing in the world as nickel sulfate, then you'd get nickel oxide. Okay, but since there is such a thing as nickel sulfide, it goes beyond the nickel oxide. It's a nickel sulfide.
I think in case of iron, you can have two iron oxide.
Only at a very specific partial pressure.
Most
If you consider what you're going to do is you could have you're going to have a constant temperature. Okay, and you're going to have an atmosphere, a gaseous atmosphere in which you have a certain oxygen pressure. Okay, now you have the reaction iron plus 1/2 O2 equals FeO, so it's going to have an equilibrium oxygen pressure, PO2 1. You're going to have FeO plus oxygen forms Fe3O4. Balance the thing out. That's going to give you another equilibrium oxygen pressure, which is higher than this one. And then you're going to have Fe3O4 plus oxygen forms Fe2O3, and you're going to have a PO2 3. So PO2, the PO2 is going up. This is lower, high. Okay. Now you got to compare these oxygen pressures to your actual oxygen pressure. So you could consider here you have a PO2, And you could have, this is PO2, this is PO2 1, this is PO2 equilibrium 2, and this is PO2 equilibrium 3. If your actual oxygen pressure is down here, then you're going to have iron. If your actual oxygen pressure is in this range, you'll have FeO. If it's in this range, you'll have Fe3O4. And if it's above here, you'll have Fe2O3. If it's exactly this value, then you will have 2 of them. Okay, so if the equilibrium oxygen pressure is exactly equal to PO2, then you will have the 2. But for an arbitrary oxygen pressure, you will never have 2, you'll have only 1. Okay. And, you could, well, clearly then, and what you want to do is then you want to write, if you still don't quite believe it, why can't I have 2? You would then have to write the exchange reaction. You would take this reaction minus this reaction, and you would find that if PO2 was less than here, it's positive. If it's greater than here, it's negative. In other words, FeO is formed, but if FeO is formed, it would be, if your oxygen pressure is up here, then all 3 of these are more stable than iron, but FeO will then react to form Fe3O4, Fe3O4 will then react to. And that's the phase rule, after you've seen, which we'll do a little bit later. Happy with that? Number 18, graphite versus diamond. What pressure is necessary at 25 degrees Celsius in order to convert graphite into diamond? Okay, so there's 2 forms of crystalline carbon. There's graphite and diamond. And at high pressure, diamond is more stable than graphite. And at low pressure, graphite is more stable than diamond. So why did we then observe diamonds at room temperature and pressure? Well, it's because once formed, the diamond has a very high activation energy. To nucleate the graphite is a very, very slow process. If you presumably waited millions and billions of years, some of your diamonds might start to, even then it probably wouldn't work. Okay, there's a nucleation energy. It's a very just extraordinarily slow process. You can't nucleate the particles of graphite. Okay, but thermodynamically, the graphite is more stable than diamond at room temperature. Graphite diamonds are formed in at high temperature, however, they would decompose back into graphite. The diamonds are formed under very high pressures and high temperatures in the earth. And then they have to come to the surface very fast. If they come to the surface slowly, they transform back into graphite on the way. Because as the pressure drops, the graphite becomes more stable. And if the temperature is very high, then the nucleation is quick, and so they transform back. So you get these things called Kimberly Pipes, where the diamonds are formed, and then somehow geologically they come to the surface very fast in some geological process. Somehow they come up where the temperature is low enough and they didn't have time to transform back, and that's why diamonds are very rare, because this doesn't happen too often. Anyway, so what is the pressure necessary at 25 degrees to transform graphite into diamond? We don't usually haven't do too much total pressure effect, but here we go. Okay, I've tried to look at it. There's different ways of looking at it. I'm doing again a thermodynamic cycle. I did these cycles before where I had 2 different temperatures and then I went around the cycle. Now I have the same temperature, but they're 2 different pressures. Okay, so here we have, this is graphite forming diamond. This is all at 25 degrees Celsius. So temperature is constant in this thing. But here I have graphite forming diamond at P0, which is 1 atmosphere. So this reaction is the standard state reaction, which is delta G standard. Here I have graphite forming diamond at a high pressure, P, and that's delta G because it's no longer the standard Gibbs energy. Okay, to be strictly correct, I've always said the standard Gibbs energy for solids and liquids is the pure material. It's more than that, it's the pure material under an applied pressure of 1 atmosphere. Now normally in material science, where you're dealing with a few atmospheres, the effective pressure is so slight that we don't have to worry about it. But if you get to extremely high pressures, then pressure will have an effect on the Gibbs energy even of a solid or a liquid. Okay, so when you're going to really high pressures, you have to consider the pressure effect. Okay, so delta G is no longer equal to delta G naught if the pressure is huge. So, but delta G is still a state property, so delta G for this reaction at high pressure is equal to this delta G plus this delta G plus this delta G. You go around the path. Delta G then is delta G naught plus this delta G plus this delta G. So what is the delta G to change the pressure of something at constant temperature? Go back through the notes that I've given you, and you have under dG is VdP minus SdT. Okay, so if the temperature is constant, dG at constant temperature is equal to VdP. Okay, so to go from P1 to P2, delta G to go from P1 to P2 is the integral of V dP from P1 to P2. Okay. So the delta G then is delta G naught plus, now you're going from 1 to P. So you're to change the delta G of the product. This is from 1 to P of V. This is the molar volume. This is the volume per mole of diamond. And you've got to lower the pressure on the graphite, so minus the volume of molar volume of graphite dP, where V is the molar volume. Okay, so delta G0 then. After the question, what was the question worded? Yeah, okay. Oh, sorry, all right. What I want to do then is I want to calculate the minimum pressure necessary. I want to calculate the pressure at which the system's at equilibrium. If you got a higher pressure, okay, the delta G standard for this reaction is positive. Sorry, the delta G standard is 2866. So delta G0 is plus 2866, which is positive. So that means that at room temperature, this reaction, at room pressure, so atmospheric pressure at 25 degrees, this reaction goes to the left. So graphite is more stable than diamond at 25 degrees in 1 atmosphere. Okay, what you want to do is you want to get, but as you raise the pressure, the delta G will become less and less positive until you reach a point at which the delta G is 0, and that will be the minimum pressure necessary to do the transformation. If you go to a higher pressure, the delta G becomes negative and the diamond becomes more stable. So I want to find the minimum pressure, so I want to find the pressure at which the delta G is in fact equal to 0. Okay, so I want to find the pressure at which delta G is delta G naught plus this integral is 0. So it's the difference of the, so the delta G naught then should be equal to this distance here, where these are the differences in the molar volumes. So this is pretty close equal to the difference in the molar volumes times P minus 1. I'm assuming the molar volumes remain constant with pressure. In fact, they don't quite, because they have compressibility is not 0, but if you compress it, the molar volumes change a bit, but that's a secondary effect. The main effect is. So I'm making the rough approximation that the molar volumes stay constant with pressure. So the molar volume of graphite is the 1 over, this is the density in grams per, liter. This is grams per liter, 12 is grams per mole. The 1,000 is to convert it to, from milliliters to liters, and that gives me liters per mole, okay? The density is given in grams per milliliter. That's the molecular weight of graphite, of carbon, which is 12, the atomic weight in grams per mole, so you get liters per mole. Okay, so that's the volume. It's the volume of 1 mole. The volume of 1 mole of graphite is 5333 times 10 to the minus 3 liters. Similarly for the diamond, you calculate the molar volume, and then you have the difference in the molar volumes here, and you calculate delta G, blah, 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 and so P is 14,700. What's happening now here is that this term The second term here is negative. The delta G0 is positive, and as you increase the pressure, this term here is bringing the delta G less positive. Because it's negative term, that is because graphite has a higher molar volume than diamond. If the molar volumes were the same, there would be no pressure effect. If it was the other way around, it would be going the other way. Now, does this make sense according to Le Chatelier's principle? If I increase the pressure on something, which phase do I stabilize? You stabilize the phase that has the lowest volume. You're squeezing it down. Okay, so graphite has the higher volume, so as I squeeze it down, I'm compressing it, and it becomes more favorable to go to a lower molar volume. Okay, so you tend to favor, at high pressure, favors the most compact, the phase with the lowest molar volume or the highest density. So you're squeezing it. Okay, so this would be the minimum pressure. Now, even if you went above that pressure at room temperature, you're not going to convert it because the temperature is still so low that you just wouldn't get a nucleation. Okay, but if you did this at a higher temperature, you would find, again, you got to go to higher temperature. Higher temperature would be there for the kinetics. Actually, at higher temperature, it favors a higher delta G0, but you have higher temperature to get kinetics, you have the high pressure for the thermodynamics. If you put the high temperature, high pressure in order to get the delta G negative, you have the high temperature in order to make the reaction faster, then you're going to get a diamond. That's how they make them industrially. And you have to reduce the temperature. Well, then you could reduce the temperature, and industrially you put high temperature, high pressure, you get your diamond. First you reduce the temperature down to room temperature, then you reduce the pressure, and then your diamond doesn't. Otherwise, if you did it the other way around, it would convert back. Actually, you have to go quite a bit higher than that, so you'd have to go to several kilobars, far more than 14. But this is your minimum. This is in principle your minimum. One last one. You have a container with 100 liters, it's empty, you enter a 0.1 mole of H2S, 0.1 mole of hydrogen, seal it, heat it to 1,000 degrees, calculate the partial pressures of H2S, H2 and sulfur at equilibrium. This is very similar to that one I did with the PCl5, PCl3, just turned around a little bit. It's a mass balance. Mass balance plus equilibrium. The sort of thing, this is what basically, okay, this is mass balance plus equilibrium. This is doing it this way so you can kind of see what you're doing. If you were taking this course back when I took this kind of a course at university, you'd be doing it this way because you wouldn't have your computer to help you out. This is exactly the same thing as Gibbs energy minimization with mass balance constraints. The system at equilibrium minimizes the total Gibbs energy under the whatever mass balance constraints you have. Mass balance constraints meaning the total amount of hydrogen is constant, the total amount of, this is closed system, so the total amount of every element is constant. Okay. If you put this thing into, try this thing in FactSage, do exactly the same question. How was the question worded? Okay, you take FactSage, take 100 liter volume, 1,000 degrees Celsius is your temperature. Okay, your reactant is 0.1 moles of H2S and 0.1 moles of hydrogen. You put that in on the first window of FactSage. You then on your, then you have to set your final conditions. So your final conditions are 100 liters and 1,000 degrees. And you say calculate, and you'll end up calculating the partial pressures. So it's calculating the partial pressures at equilibrium under the constraints of the total amount of hydrogen and sulfur is whatever you put in. And it's doing it by minimizing the total Gibbs energy. Okay, but what it's doing is equivalent to what I'm going to do here, and I think just looking at it this way also gives you a little idea. So I take H2S, H2 and sulfur, and I'll remember it's the same thing as I did before. I make up a table where the entries in the table are moles. This is the entrance, this is the beginning, and this is when equilibrium is achieved. So the problem says that I put in at the beginning, I put 0.1 moles of hydrogen and 0.1 moles of H2S and 0 moles of sulfur into the box, and the thing reaches equilibrium. So it reaches equilibrium according to this reaction. So if this reaction proceeds to the right with the formation of 1/2 x moles of sulfur, it will also form minus x mole, it'll form x moles of hydrogen. So at equilibrium, the total amount of hydrogen will be the initial amount plus x, and you'll have 0.1 minus x moles of H2S at equilibrium by the mass balance. Total number of moles at equilibrium, if you're doing this kind of question, the total number of moles at equilibrium is not always equal to the initial. Initially you have 0.2, but afterwards you got more than 0.0. So this is the total number of moles at equilibrium. Then you do Dalton's law. Partial pressure of H2S is the number of moles of H2S divided by the total number of moles times the total pressure, the same thing for all three of them. And the next thing you do is you write out the gas law. P total V is N total RT. And then you think a little bit. And you say, okay, P total, this is N total. I have N total. RT, I know what T is. That's R. V is given. Okay, so blah, blah, blah. So I can figure out what X is. Okay, so then putting X back into this equation here, I can calculate the partial pressures. And from the partial pressures, I can calculate the equilibrium constant. And what did I ask for? Okay, calculate the equilibrium constant. No, sorry. I have all the partial pressures in terms of X now. So delta G is minus RT log K, so that's K. So I can calculate what X is by plugging all these back into the equilibrium constant. Then I want all the partial pressures, so now I put X back into these equations along with the total pressure, and I get all the partial pressure. So this is taking your mass balance into account. This is taking your mass balance into account. This is taking your chemical equilibrium into account. This is your ideal gas law. And this is equivalent to minimizing the total Gibbs energy under mass constraints. That's how you sort of have to do it. Okay, so that's an awful lot about Gibbs energy and so on, but the concepts here are fundamental, and be sure you understand the concepts of these things. Okay, let's take a few minutes. One, two, three, go.